In section 1.4, we want to look at something that we refer to as isomers. Now, isomers are simply situations where we have more than one possible Lewis structure for a given molecular formula. There's just more than one way to arrange those atoms. And these molecules are said to be isomers of each other. The example I have given here is ethanol and dimethyl ether. These both follow the rules that we learned in the last section when drawing Lewis structures. But what's different here is obviously what's different here is the connectivity of the atoms. So we've got carbon, carbon, oxygen, whereas this one is carbon, oxygen, carbon. Now, typically, the hydrogens, there's not a lot of flexibility about where you can put the hydrogens. Sometimes we'll see a little bit of flexibility on that, but that's a rare exception. Most of the time, it's a different backbone, the atoms that are in the middle. And so what we want to do is we want to look at what these different isomers are. Now, there are different kinds of isomers that we're going to be looking at this semester, and what we're going to start with is something that we refer to as constitutional isomers. Constitutional isomers have the same isomers that have different connectivity. Later in the course, we're going to see something that is called stereoisomers, and in fact, a little bit later in this chapter, I will show you an example of a stereoisomer. So we want to look at problem number 1.46. So here is number 1.46. I'm going to zoom in a little bit. All right. So on 1.46, we've got C3H7Cl. And when it comes to drawing out the structure of this, the carbons are going to be the backbone. And so there's, if you have three carbons in a row, really there's only one way to put three carbons in a row. If you change the order, that doesn't really do anything. And so here we've got our three carbons in a row, and really the difference is where do we put the chlorine? Now, obviously, we're going to fill in hydrogens wherever we can, but we're going to determine where do we put the chlorine. And so I'm going to just put the chlorine on the end here, and that is one example. And so you'll see that we have 7 hydrogens remaining. So I'm just going to fill in those hydrogens. 1, 2, 3, 4, 5, 6, 7. And that's one of our isomers. For the other isomer, again, we're going to draw the 3 carbons in a row, and then we'll put the chlorine on that second carbon. All right. And I should go ahead and put these lone pair electrons in, although you don't necessarily have to, but just so it's all clear. And when we put in the remaining hydrogens now, so we can put 1, 2, 3 hydrogens there, 1 hydrogen on that carbon, and then 3 hydrogens out here. Now, sometimes people, when they look at these, they ask, well, what if I put the chlorine here and the hydrogen there? It turns out that would be the same compound. If you put the chlorine there and the hydrogen there, that would be the same compound as this. When we get to the shapes of structures a little bit later, you'll see that these 3 positions are identical, that there's no difference between, whether we put it up here, down here, or on the side. Same thing here. There's no difference whether we put the chlorine up here on the top or whether we put it down on the bottom. Okay. The other thing that sometimes people ask is, well, what if we put the chlorine over here on this first carbon instead of on the third carbon? Well, it turns out that would be identical to this isomer. So these are the only 2 isomers for C3H7Cl. All right. For this next one, you'll find that when you start to do this, that there's you can't do this without putting a double bond in somewhere, and so or a ring, and we'll talk more about that as we get a little bit further in the class, but I'm just going to put one here. So carbon, carbon, oxygen. Okay, so carbon, carbon, oxygen. And when we start, you'll see there's only 4 hydrogens here. And when we start putting in those hydrogens, there's just not a whole lot of possibilities without putting in a double bond. So I'm going to go ahead and do one of the isomers. Okay, that's one of the isomers. It turns out that particular isomer isn't very stable, and it will actually be in equilibrium with a different isomer. And so I'll go ahead and draw that other isomer here. And that other isomer is going to be carbon, carbon, oxygen. All right, and 1, 2. And let's see, that hydrogen is still there, but we end up with a double bond going to the oxygen. And we'll see that that is an isomer. Turns out these are in equilibrium with each other. They are not resonance structures because the hydrogen is in a different location here. So here the hydrogen, we have one hydrogen on the oxygen. Here we have no hydrogens on the oxygen. That hydrogen actually moves over to that carbon that's one step away. So these are in equilibrium. And you might just note this word down. I'm going to write it here. So these are called tautomers. All right, and we're going to talk about, so these two are called tautomers of each other. We will talk about tautomerization in a later chapter in this text. The other possibility for this particular molecular formula is where we put a ring in. All right. And this is called ethylene oxide. It is an epoxide. It's used extensively in industry for a lot of different things. It's a monomer for polymerization, all kinds of interesting properties for epoxide. All right, and those are our 3 structures. We'll find that this is not going to be in equilibrium with these other ones. This is just a different kind of compound, but interesting compounds nonetheless. So 3 different isomers. Now, if on your own you're having trouble coming up with those different isomers, particularly with a double bond or a ring, don't worry about that right now. You will get better at this as we move along. For the next one, we have 4 isomers, and the 4 isomers of the C3H9N, and I will go ahead and draw the different isomers that we have here. So again, it's best just to start with the backbone. The possibility is that we've got 3 carbons in a row, and then nitrogen. And now just go in and fill in all of the hydrogens. We have 9 hydrogens to work with. So 1, 2, 3, 4, 5, 6, 7. And if you remember, nitrogen typically has 3 bonds going to it, so we can put in 2 hydrogens there. And I'll go ahead and put that lone pair of electrons on the nitrogen. All right. Next, we want to look at what if that nitrogen is on the second carbon, kind of like what we did up here with the chlorine. Here we have the chlorine on the end, here we have the chlorine in the middle. Well, we still have that same possibility where we've got carbon, 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 and then nitrogen there. Well, again, we can fill in all of those hydrogens. So 3, 4, 5, 6, 7, and then 8, 9. And we'll go ahead and put that lone pair of electrons on there. All right, so those are constitutional isomers of each other. We've got another constitutional isomer that we can draw. We've used up the possibilities where all 3 carbons are connected. So now we want to look at the possibility where the nitrogen is in the middle of those carbons. So we'll have carbon, carbon, nitrogen, carbon, and we'll put those in 1, 2, 3, 4, 5, 6. We'll go ahead and put that lone pair in. 7, 8, 9. All right, and that is again a different isomer. And then there's one more, and if we had switched these two, it would be the same structure as this. So like if I had carbon, nitrogen, carbon, carbon, that would be the same as this. So instead, we can have the situation where we've got carbon, nitrogen, carbon, and carbon. And then we'll just go through and put the hydrogens on all of those carbons. And there's a lone pair of electrons on that nitrogen. And that is our fourth isomer. All right. Later in the semester, we'll talk about how these have different properties and different boiling points and melting points and things like that. Kind of a cool topic to look at. All right. So we want to go back to our presentation and look at our next topic, which is looking at exceptions to the octet rules. Now, I'm going to show you a couple of exceptions to the octet rules. We're not going to get into great detail on that, and I'm not working any problems on that right now. But it is important to be aware of what those exceptions are. We will find that elements in groups 2A and 3A have a tendency to not have a full octet. So examples of this would include beryllium. Here's beryllium hydride, so BeH2. Here's boron trifluoride. That is an exception. You'll notice this one only has 4 electrons around beryllium. This only has 6 electrons around boron. And we will find that happens quite a bit with groups 2A and 3A. It happens with aluminum. If you have aluminum chloride, you'll have a similar type structure that goes on there. And so that is one of the types of exceptions to the octet rule. We'll find that elements that are in period 3 or lower on the periodic table, so row 3 and lower, that they can have more than an octet. And so here are a couple of examples. This is DMSO, which is a very widely used solvent for a lot of different applications in synthesis. You'll notice that sulfur has 10 electrons around it, so 4 bonds plus a lone pair of electrons. Sulfuric acid, the best way to draw the sulfuric acid structure is to draw that where you have 6 bonds going to that sulfur. And we'll see it with phosphorus. Here with phosphorus, you'll see that there are 5 bonds going to that phosphorus. That gives you 10 electrons. Well, we're going to find that things that are in period 3 or lower on the periodic table can do that. Now, let me just go over to the periodic table just so everybody's clear here. So we'll see it happens with phosphorus, with sulfur. It can even happen with chlorine, but we'll see it with arsenic, selenium, bromine, and there's even a few compounds of xenon and krypton that this can happen with. And we'll see it happen with some of these down here as well. But sulfur and phosphorus are the ones that we run into the most often in this class. All right. And then we'll find that there are structures that have an odd number of electrons. In odd numbers of electrons, we have unpaired electrons, and we'll talk about unpaired a little bit later. These are radicals, and this is just an example of a radical. It tends to be quite reactive, but you'll see that there are only 7 electrons around that carbon. So 2, 4, 6, and then 1 more for the 7. And that is a valid Lewis structure for that methane radical, the methyl radical. All right, so those are exceptions to the octet rules. We'll run into those as we move forward. You need to be aware of those. All right, we now want to talk about resonance structures. And you probably had a brief introduction to resonance structures in your General Chemistry 1 class, and I want to get into it in more detail. So resonance structures are 2 or more Lewis structures that have the same placement of atoms, but a different arrangement of the electrons. And when we say a different arrangement of the electrons, we have the same connectivity. So your single bonds are all in the same place, but your second bond, which is a pi bond, again, we'll talk about pi bonds here coming up shortly, and lone pair electrons can move around. We'll also find that if there are charges, that those charges move around on the structure. When we look at this and we say, okay, well, I've got this anion, it's got a negative charge on it. Which of these is the true structure? Is the true structure going to have the double bond with the oxygen and the negative charge on the nitrogen, or with the negative charge on the oxygen and the double bond going to the nitrogen? And the answer is neither. Neither one of those is the true structure. The true structure is somewhere in between. Now, it's not going to be like a 50-50. It's not going to be like half this and half this, because these are not equal resonance structures. However, when we look at that, we can come up with what that in-between structure looks like. And so I'm going to show you what that looks like here in just a second. All right, so the structure that we're going to come up with that's somewhere in between, we will call that a resonance hybrid. The resonance hybrid, as I mentioned, is somewhere in between. You'll see here that we've got a double bond between carbon and oxygen, and here is a single bond. Well, in our resonance structure, our resonance hybrid rather, we've got about 1.5 bonds between carbon and oxygen. Here we've got a double bond or a single bond between carbon and nitrogen, a double bond between carbon and nitrogen. Well, there's about 1.5 bonds between carbon and nitrogen here. On this structure, on the structure on the left, we have 0 charge on the oxygen, 0 formal charge. Here we've got a -1 formal charge. So that means there's going to be part of a charge. We represent that partial charge, the partial negative, by putting a lowercase Greek letter delta with a minus. So delta minus. In a similar fashion, on the nitrogen, we've got -1 here, 0 there. That means that we will put a delta minus on that nitrogen. So the hybrid has characteristics of both resonance structures. The thing is that a hybrid, the resonance hybrid, is not a valid Lewis structure in and of itself. When we're drawing structures, we like to draw Lewis structures. The hybrid is just a way of representing what the average of those resonance structures is going to look like. All right. We will find that when we can draw resonance structures, we say that the electrons are delocalized. And by that, if we look here, we've got a negative charge on the nitrogen here, but on this one, the negative charge is on the oxygen. That means that the negative charge is actually spread out over 2 atoms, partial negative on the oxygen and a partial negative on the nitrogen. What that means is that whenever you can delocalize electrons, particularly if it's something reactive like a negative charge, then that stabilizes that structure and makes it much less likely to be reactive. So resonance is going to give you stabilization. Now I say resonance equals stabilization, but really it gives you stabilization. So resonance will impart stabilization on your structure. Now, there's some basic principles that we use when we're doing resonance theory. And our first principle is that resonance structures are not real. So resonance structures in and of themselves are not real, because the true structure, electrons are weird things, that the electrons are not, they're not particles that are in a particular location. They're spread out over a region. Well, that means that each individual resonance structure is not something that you could observe at any point. And only the hybrid structure gives you an idea of what it really looks like. The problem with hybrid structures is that they're not valid Lewis structures. So that's one of the limitations of Lewis structures, is that they're not real. And so our resonance structures are not real. Now, here is an analogy for this, and I thought this was a funny analogy, one that I pulled out of a different textbook. But you'll see here on the left, unicorns are not real, dragons are not real. But if you take the hybrid between those two, you get something that's maybe a little bit less exciting, although I'm sure if you saw one in person, it would be plenty exciting. And that would be a rhinoceros. And that is the real structure. Sometimes the real structure doesn't have quite the appeal that the resonance structures themselves do. That said, this is just an analogy. You don't want to take it too far. Our second principle of resonance theory is that resonance structures are not in equilibrium with each other. There's no literal movement of the electrons. We will say that we're moving the electrons, and I'm putting quotes there around movement, but really what's happening is that those electrons act like a wave. So you can have part of the electron density in one place and part of the electron density in another place. So resonance structures are not real. All right, they're not real, and they're not in equilibrium with each other. And another important concept is that resonance structures are not isomers. Resonance structures only differ in their arrangement of electrons. So they only differ in their arrangement of electrons. And so here I've got two resonance structures of this ion, so CH3CO, and there's a positive charge that's on that molecule. And you'll see that on this one, we've got a triple bond between carbon and oxygen, and we end up getting a positive charge on the oxygen. Whereas on this resonance structure, we've only got a double bond, and we end up putting the positive charge on the carbon. Well, those are resonance structures, and the true structure is going to be something where we get partial positive on the carbon and partial positive on the oxygen. And so that's what we mean. You'll notice, though, that the atoms are all in the same order. They're all connected in the same way. And that, neither one of these is the true structure, and that the electrons are not literally moving when we're doing this, because the true structure is just the hybrid. So we want to look at number 10 on the in-class assignment. And for whatever reason, when I printed it out, now I know it's on there when you have it on the digital copy, but for whatever reason, when I printed this out, the structures didn't show up. So I've just written them out here, and I'll deal with that at a later point. If you're having trouble, just look at the digital copy and you will see the structures there. So classify each pair of structures as isomers or resonance structures. If they're resonance structures, all the atoms are going to have the same connectivity. If they are isomers, then the atoms are going to be in a different order. Well, when we look at this, we got NCO, and here we have CNO. So the central atom is different here, so that means that these are not resonance structures of each other. These are isomers. All right, so those are isomers of each other. Here we've got, let's see, here we've got, so HOC. This is actually the bicarbonate ion. This is the ion that you get. This is the ion that is in like sodium bicarbonate, baking soda that's in your house. So this is the bicarbonate ion, and you'll see we've got HOC and then an oxygen there and an oxygen there. Same thing over here. The only thing that's different is that on the structure on the left, we've got the negative charge on this upper oxygen, and on the structure on the right, we've got the negative charge over here on the bottom right oxygen. And you'll also notice that the double bond has switched positions. So these are resonance structures. All right, so those are resonance structures of each other. All right, so let's go back to our presentation, and we want to look at how it is that we draw resonance structures, and how do we keep track of the electrons when we're drawing the resonance structures. So when we're drawing resonance structures, we have a set of rules that we're going to use. I believe there's 4 rules here. And those structures, rule 1, 2 resonance structures differ in the position of multiple bonds and non-bonded electrons, so lone pairs. And we saw that on the example that we just looked at for bicarbonate. The placement of atoms and single bonds always stays the same. So you're going to have the same connectivity, and if there's at least one bond, then you have to have at least one bond in the other structure as well. And so here you'll notice that going back, this is a similar structure to what we saw a little bit earlier, but you'll notice here that the position of the double bond changes. Here it's between the carbon and oxygen, whereas over on the right it's between carbon and nitrogen. And that the negative charge, or the extra pair, lone pair of electrons, so we have a lone pair of electrons here, an extra on the nitrogen. That gives us the negative charge on the nitrogen. And over here on the right, we've got the extra pair of electrons on the oxygen, giving us the negative charge on the oxygen. So we have to have the same connectivity. So each atom is connected by at least one bond. And the only things that are moving around are the pairs of electrons and the second bond, the double bonds. If you count, you'll see that there's still the same total number of valence electrons in each structure. Our second rule is that when we're drawing resonance structures, they have to have the same number of unpaired electrons. You remember a little earlier, I called it unpaired electrons, I called those radicals. Well, radicals have a whole different kind of reactivity than non-radicals. And so here, our structure on the left, we don't have any unpaired electrons, whereas our structure on the right, we've got 2 unpaired electrons. Well, these are not resonance structures of each other. It turns out that that structure on the right, structure C, is actually an excited state. If you were to hit this with just the right frequency of light, probably some ultraviolet light, it would cause the electrons to go to an excited state, and you could create this. But again, this is not going to happen in normal situations. These are not anywhere close to each other in energy. So these are, like I said, not resonance structures. If you have a different number of unpaired electrons between one and another, they are not resonance structures. Rule 3, resonance structures have to be valid Lewis structures. Now, this is not true of the resonance hybrid, but it is true of the resonance structures themselves. So hydrogen has to have 2 electrons going to it, which pretty much means a bond if it's in a molecule. And the second row elements, which include the carbon, nitrogen, oxygen, and fluorine, they have to have 8 or fewer electrons. Now, it is possible to have less than 8 electrons, but you cannot have more than 8 electrons around a period 2 element. So, for example, here we've got this particular structure. This is the same one that we were looking at a moment ago, but we've drawn this faux resonance structure. It's not a real resonance structure because you'll notice that there are 10 electrons around that carbon. Well, that is forbidden. That is against the rules for doing resonance structures. All right, so not a valid Lewis structure there because of the 10 electrons around carbon. If you ever are drawing something and you find that there are 10 electrons around carbon, nitrogen, oxygen, fluorine, any of those, here I'm going to switch over to this. So any of these, boron, carbon, nitrogen, oxygen, fluorine, if you have more than 8 electrons around them, so 10 or more, it is not a valid structure. You just can't do that. Okay. So now we want to look at what we refer to as curved arrow notation. This is an important concept and something that I really stress throughout this semester and next semester. This is something that if you're going to be good at organic chemistry, then you have to be good at curved arrow notation. It is a convention that we use that shows how the electron position differs between the 2 resonance structures. Now, I use the word movement. It says curved arrow notation shows the movement of the electron pair. I should probably put movement in quotes there. And the reason I should put movement in quotes is that the electrons themselves aren't literally moving. Remember, between resonance structures, the true structure is an average of them. We don't have equilibrium between the resonance structures. But in terms of what we look at from one structure to the next, we can show, well, where did we get those electrons? Are we accounting for all of the electrons? Well, that's what curved arrow notation is all about. So we'll find that the tail of the electrons always begins at some pair of electrons. That pair can either be a bond or a lone pair. And in fact, in a later chapter, we'll get to where we can have single electron movement, and we use a slightly different kind of arrow, but we'll save that for a bit. The head points are where the electron moves to. If you're making a lone pair, then the atom or the arrow will end up at an atom. If, on the other hand, you are making a bond, then the arrow will end up at a bond. So for example, this lone pair that is on carbon is going to end up as a bond between these two carbons. So there's a double bond there. So that's where you get that second pair of electrons between the two carbons. The second bond between carbon and oxygen is going to get kicked out to the oxygen, and you will end up with a lone pair on the oxygen, an extra lone pair. Now, one of the kind of quick and easy ways of doing this is if you have a positive charge, then the arrow is going to start away from that positive charge and move towards it. So you'll see here where we've got this positive charge on carbon. Well, we can move this arrow, move this pair of electrons between carbon 1 and 2 and go to between carbon 2 and 3. So when you have a positive charge, the arrows are going to be moving towards the positive charge. Now, not necessarily exactly to the positive charge, but towards it. When you have a negative charge, you typically start with a negative charge and move away from where that negative charge was. So here we move to form that bond and then kick that one out to the oxygen. So again, if you have positive, move towards the positive charge. If you have negative, start with a negative and move away from it. Let's look at number 51 and 52 on the in-class assignment. So here's number 51, and this one is pretty easy, but we got to start somewhere. So this one's pretty straightforward. And you'll see that on this one, we've got carbon, that this carbon doesn't have a full octet, so it can accept some electrons. And we've got a pair of electrons that's on the nitrogen. And then over here, we end up with a double bond between carbon and nitrogen, and we end up with a positive charge on the nitrogen. So we're always going to put the arrows on the structure that's on the left. So as we move across, it's the arrow, think of the curved arrow notation as instructions for how to get from here to here. So since we have a pair of electrons that's on the nitrogen and we're trying to make this bond, we're going to take that pair of electrons and draw it so that we have an arrow going to the bond. Now notice that I pointed it to the bond. You don't want to go to the atom, you want to go to the bond. All right, and that's it. That's it. We don't need to take this one and go back. Now, if I had a third structure, then we could draw arrows on it to show how to get that third structure. But you don't typically do the arrows to go back. All right. Here you'll notice that we've got a double bond. You'll also notice there's no negative charges on this. But when we look at our resonance structure, there's a negative charge on the oxygen and a positive charge on the nitrogen. Well, the way that we got that negative charge on the oxygen is that we had to kick the pair of electrons out to that oxygen. So we're going to take this pair of electrons that is the second bond, and we're going to go out to the oxygen. Now, you don't necessarily have to curve all the way around. You can just go straight to the atom. But you want to be clear when you're drawing these. And for example, when I'm doing my test, there is always a short answer portion of the test where you have to do at least a little bit of drawing of resonance structures and doing some curved arrow. You will pretty much on every test see curved arrow notation. So you have to know how to do this, and you want to be clear about where the electrons are going. Now, if I just stop there, we would end up with a positive charge because we'd only have 3 bonds going to carbon. We'd have a positive charge on carbon, a negative charge on oxygen. But instead, what we're going to do is that we are going to take that pair of electrons that is on the nitrogen and make the second bond between carbon and nitrogen. So we will draw that one to form that bond. And that's how we get this particular structure. We are going to practice this a lot. So if you're not getting it yet, don't worry. You will see this a lot. All right. So let's look at 52. We've got a couple of resonance, we've got one structure here, and we want to draw the resonance structure over here. Let's see. This is called. This is the methyl diazonium ion. In case you're curious. That methyl diazonium, not very stable, not something I'd want to keep hanging around my lab or anything. But you'll notice that we've got one of the pairs of electrons here that's the third bond, and we're going to make a lone pair of electrons on the nitrogen. So we would have CH3, nitrogen, we'd put a lone pair there, and then we'd be left with a double bond, nitrogen, and still a pair there. As far as the formal charge, you'll see that now the formal charge on this nitrogen is 0 because nitrogen is in group 5. There's 3 bonds and 2 lone pair electrons, so 1, 2, 3, 4, 5. So 5 minus 5 gives us 0, whereas this one owns 1, 2, 3, 4. So 5 minus 4 gives you a positive 1. So we'd have a positive 1 on that nitrogen. It turns out that both of these resonance structures are important with the diazonium ion. So both of those resonance structures are important. The true structure is somewhere in between. All right. On this one, you'll see that we've got this negative charge on the oxygen, and we're going to make a new, we'll make a new double bond between carbon and oxygen. So I'm going to put a double bond there. All right, that takes care of the first arrow. Now you'll notice that we have to move this other bond, this other pi bond that's between these 2 carbons. We're going to move it out to these 2 carbons. So there'll be a single bond, CH, and then a double bond, CH2. And when we do that, we are going to end up with no formal charges on any of the atoms. So again, this one became the pi bond between carbon and oxygen to form that carbonyl, and that this carbon-carbon double bond, one of the pi bonds moved over, and we formed a bond between those 2 carbons. All right, so that is for that particular resonance structure. Let's go back to our in-class, our presentation rather. We'll find that there can be atoms that don't have octets, and we saw a couple of those on this previous thing where there were certain atoms that didn't have a full octet. All right, so resonance structures can have atoms that have fewer than an octet. For example, this is the structure acetone. So this is acetone. Acetone is a commonly used solvent. I've got some right here in my shop that I use for cleaning certain things, cleaning certain bits of equipment. It's good at removing grease and paint and things like that. You also see it in nail polish remover. And that you can draw a resonance structure of acetone where you move that pair of electrons out from being the double bond between carbon and oxygen. You put a negative charge on the oxygen and a positive charge on the carbon. Well, that is a valid Lewis structure. If you look at the hybrid structure of acetone, there is a partial positive charge on that carbon. That carbon-oxygen bond is quite polar. However, we'll find that for our second row elements, they can never have more than 8 electrons. And I've already mentioned this, but it's worth mentioning again. Don't ever put more than 8 electrons around period 2 elements. So don't do it with carbon, oxygen, carbon, oxygen, nitrogen, fluorine, boron, any of those. You don't want to put more than 8 electrons around it. Now, just because we can draw both of these structures doesn't mean that they are equivalent. So often we will have something that we consider a major contributor versus a minor contributor. When there are two different structures, the hybrid structure looks like the better structure. It looks more like the better structure. And so, for example, here, this one is not acetone. This one is this is acetaldehyde. It's got 2 carbons and it's got this carbonyl, and you'll see it's an aldehyde because it has a hydrogen on the carbonyl. We'll talk about functional groups later. Don't worry if you're not familiar with those. Over here, we have that carbon oxygen. There's a positive charge on the carbon, negative charge on the oxygen. And you'll notice that we don't have a full octet on the carbon. Well, the major structure is going to be, again, the better structure is the major structure, and any other structures are going to be considered minor contributors or minor structure. So the major contributor and the minor contributor, the major one is the better one. We will find that the better structure is going to be the one, yes, and of course the resonance hybrid will have characteristics of both. So here is our resonance hybrid. It'll have characteristics of both, but it is going to more closely resemble the major contributor. So, so while there is a partial positive charge on carbon and a partial negative charge on oxygen, there's quite a bit of double bond character here. So I mean, I couldn't give you a percentage. I could guess maybe 90-10. It's definitely not a 50-50. All right. And so when it comes to evaluating which one is going to be the better structure is typically going to have fewer charges and will have most of the atoms, if possible, will have a full octet. So if you have a structure that doesn't have a full octet, it's probably going to be a minor contributor. And if you've got one that has, now that's not always the case, but if you've got one that has no formal charges versus one that has formal charges, the one with the no formal charges is more likely to be the better structure. All right, so let's go to number 40 on the in-class assignment. For each pair of resonance structures, use a curved arrow notation to indicate the movement of electrons. So this is similar to what we did up in number 51 that was up here. But in number 40 here, we're going to do something similar here. So for each pair of resonance structures below, use the curved arrow notation to indicate the movement of electrons. Also label the major contributor and explain why it's a better resonance structure. Okay. So here we've got a carbon with a positive charge. We've got a nitrogen with a lone pair of electrons. Remember, when we have a positive charge, we typically move the electrons towards that positive charge. So we're going to start with that pair of electrons on the nitrogen and go to the carbon-nitrogen bond to give us that carbon-nitrogen double bond. In doing that, it does give us a positive charge on the nitrogen. All right. But we're trying to figure out which one is the major contributor. The major contributor is going to be the one that has, since they both have a positive charge, the major contributor is going to be the one that where atoms have a full octet. You'll notice on this structure, the carbon only has 6 electrons around it, so it doesn't have a full octet. Whereas on this one, the carbon does have a full octet, as does the nitrogen. So we're going to call this one our major contributor. All right, so that is our major contributor. And then the reason is because it gives carbon a full octet. All right, for this next one, we've got carbon has a negative charge, the carbon-carbon double bond there. And then over here on this side, we've got the carbon-carbon double bond and the negative charge on that carbon. So here we're really just moving around that negative charge and moving around the lone pair of electrons. Remember, when you have a negative charge, it's best to start your resonance structure at that negative charge. So we're going to start your curved arrows at that place. So we're going to draw an arrow from that pair of electrons that's on the carbon and make the second bond between these two carbons. And then we'll have to take this pair of electrons, that's that second bond here, and it will go to that carbon. Now, as far as which one is the major structure, these are equal structures, right? I can't spell, so structures. So these are equal structures here between these two. And the reason is that these are essentially the same thing. Here we've got the negative charge on this carbon, so CH2 it has a negative charge, and here it's just sort of the mirror image of it. So these are equal structures. That means there's not a better structure. There's not a major structure for that. All right. So let me see for a second. All right. So at this point, before we go on to the next section, I'm going to stop the video and we'll put that next section up as a different video.